Welcome, Troy.
Perfect. Thank you. Hey, thanks, everyone. Thanks for coming along to DataEngBytes, and thanks for not making me fail against the competition of a little yellow duck. Hi, everyone. Welcome to the talk today. We're going to talk a little bit. We're going to spend the next 30 minutes talking about anomaly detection using a tool called Apache Flink. A quick look at what we're going to talk about today, just a little introduction about who I am, a little bit about Aiven. We're going to talk about, what is an anomaly and what is Flink, obviously, as part of the process. We're going to talk a little bit about some of the main concepts that you have to sort of, introduce yourself to as you start to work with Apache Flink. We'll see if we've got time at the end for the obligatory demo of any one of these kind of things, and we'll sort of have a look at that. And I'm hoping to leave you with some resources about how to get more. The idea today is to whet your appetite, and we can go further from there. So as introduced, my name's Troy. I'm a staff solution architect for Aiven. It is either Aiven or Aiven. Fun fact about our business, there's 4 co-founders. Never start a business with 4, because every time you vote on how to do something, it turns out to be 2 and 2. And so they're evenly split down the middle on how to say that. Staff solutions architects at Aiven. I run the solution architecture group for Asia Pacific. I also spend a lot of time talking to our customers about all the various open source services that we operate and helping them get the most out of what we do. The business itself was founded in Finland, in Helsinki. To be precise, we're still headquartered in Helsinki. One of the main drivers behind the business was to give back to the open source community. We're very, very passionate about open source technology at Aiven. So much so that the only services we operate are the vanilla downloadable open source packages. And when we need to make changes to those packages to make them work, we actually commit that back upstream. And so we've got about 20 odd developers at the moment in Aiven that are committing to the various projects that we run. So everything that you see today is absolutely obtainable and downloadable using the open source technology. And that really is the goal. We want to take a curated set of open source services, and we've got a number of different data services. You can think across the relational, non-relational, streaming services, analytics services. Operate them across all the public clouds that exist today, and take that operational burden from you and operate this effectively as software as a service in your public cloud or in ours. We really don't care on how we do that. Okay. We're going to talk a little bit about a really specific part of our platform today. So like the obligatory big, this is all the things, the fun things that we add around the open source services. We're going to hone right in on the streaming ecosystem today. And the 2 projects in particular, Apache Kafka and Apache Flink. And I'm going to talk about these in the general open source sense of the terms, but when we get to the demo, you'll see that I'm running them in the fully managed service that we offer. Okay. So let's start from the very beginning. What is an anomaly? The first thing that's kind of interesting, maybe the less helpful definition from the dictionary, is it's something anomalous, which was an interesting thing. The thing I also learned about conference presentations is try not to choose a topic on a word that you struggle to say. So for the last 3 days, I've been struggling and practicing my pronunciation of anomaly. Let's give it a data engineering lens and focus in a little bit more. And we're going to talk about an anomaly as a data point or an odd data point that sits outside a normal distribution, a pattern of data, something that's 2 standard deviations for the mean. There's some implications behind that sentence. The first implication is you have a pattern, right? Do you know the pattern of the data that you're getting? The second implication there is that you have some capability to examine each data point individually against said pattern, and potentially you might want to take some kind of action, and that's exactly what we're going to talk about today. You'll see people that do this in 2 ways. The first sort of way that we're looking at today is pretty simple. We're going to take some kind of heuristic about the data. We're going to talk about a fleet of IoT devices. We're simply streaming the metrics out of that fleet of IoT devices. We're looking at the CPU utilization, and we're going to run a time window that says if any of these devices of an average over 30 seconds have an 80% CPU utilization, we should do something about it. Some kind of predictive maintenance scenario, for example. But you might have a fleet of things that you've deployed for the first time and you don't understand the pattern. This kind of is a really interesting use case for streaming analytics, because you can sort of feed that into some kind of linear regression or machine learning type model building algorithm and see if you can identify a pattern first, and then migrate and evolve your streaming processing application into, I've now discovered a pattern, I can now start to look for anomalies against that pattern. So that's sort of the interesting use case we're looking at. Let's talk a little bit about Apache Flink. What is Apache Flink? A framework for stateful computations over data streams, which is a very nice and succinct way of describing it. And you think about data today, and like most data can be thought of in some concept of a stream. Right now, there's a whole bunch of cars going over the Balti Bridge, and they're, the E-tags, or you guys use license plate reading down here. I'm actually from Sydney, so don't hate me too much. And those kind of things happen fairly regularly. And it's a stream of data, and you want to process that. You probably want to read the number plate and charge an account, right? And that's that concept of a stream. You're clicking buttons on your phone, people are on your website, you've got an IoT sensor coming anywhere. Like, a lot of data today is created in streams, and it comes from all these different places. It can be either real-time or historic kind of data. And Flink is an excellent tool for being able to make these stateful computations. The idea that you can sort of capture a window of state, some kind of complex event processor, count things, do averages, those kind of things. These things all have state, and we'll dive into that in a sec. So a couple of use cases that are really interesting that you can deploy out into your business around a stateful processor. The first thing is this event-driven application. This is exactly what we're looking at. The idea that I can take events as they come into my world, I can look at them. If they're out of some pattern, if they violate some heuristic, I can take an action. Okay, I'm going to have an application that's driven and fired off by this event. Some excellent examples: the classic fraud detection use case that probably everyone's really familiar with, this rule-based alerting scenario that we're going to talk about today, or we are talking about today, and then some more sort of interesting things. One of the things when I was researching for this I found interesting is a event-based application on a business process. So maybe you've deployed a business process and you can take an event on the absence. Like, if your count of steps, or if your time in a business process between step 1 and step 2 takes longer than 2 days, automate something, fire something, do some kind of alerting. Really interesting kind of use cases. The second sort of use case they talk about, like analytics use cases. It's similar to taking kind of actions on an individual event, but more taking actions on a group of events in real time. Some classic examples of this are things like quality monitoring on a telecommunications network. So you'll see your telcos, they say, hey, we guarantee there's X amount of download speed per hour or something like that. And so you can run a stateful application across your monitoring all those things and say, hey, if that average has fallen below, can we do something about it in real time to make sure we meet our quality of service things? Another interesting use case here is A/B testing. You want to push out some A/B testing into your mobile app or onto your website, for example. You can build a stateful analytics streaming application that gives you real-time feedback on how those things are going, so you don't have to wait a day or a week to have those 2 versions in production to get some instant feedback. And it's quite useful, especially if you push something out that's pretty broken and you're sort of seeing some massive things. The third one about that is just a data pipeline. So the idea of enriching, filtering, merging, those kind of things on data as it goes to different use cases. Great example here is you've got a database that sits in your warehouse. You want to take this stream of events off your database using some kind of change data algorithm, pipe it through your application, and maybe update your search service on your online web store, for example. So you've got like a real-time product search on your web store that replicates your state of your database in your warehouse. One thing that we see customers use this for fairly regularly is to take a Kafka topic or a selection of Kafka topics that sit in their production world and deliver that to their developers for testing. But in the process, do some stuff with the data, anonymize it, filter it, do those kind of things to make sure you get like a real world testing set of data on a non-production data cluster for Kafka. So it's that kind of thing. Every industry that you can think of has probably got a use case for this, folks. I don't know who's who in the room and who does what, but the classic financial services use case. Some of the more interesting ones for me that I found that I found fascinating to think about is like ag tech. You can start to apply models and anomaly detection to herd of cattle or a field of plants and detect things like disease or pests and stuff, and go in and take action really quickly on that. Kind of interesting use cases as well. The predictive maintenance across manufacturing and those kind of things, stock levels in retail, real-time sales data. It's kind of handy to see the sales in real time to see if you need to start to push or modify processes on your website. So what is Apache Flink? So at the end of the day, as a data engineer, you're going to create some kind of job. Okay, it's the unit of processing. It's where your business logic lives when you deploy something in Flink. And you deploy this Flink job. What do you deploy it into? Apache Flink usually gets deployed in a clustered configuration. It's definitely a highly available service in our world. But that's one of the massive advantages about Flink. Out of the box, it usually comes highly available and extremely fault tolerant. And it's the way you do that, it sits out, you take a cluster, one of those nodes in the cluster is your job manager, your master node. And it's in charge of doing things like, receiving the jobs and breaking those jobs down into individual tasks or operators, and then deploying those operations onto task managers. And so you can get a real excellent spread, like you can get parallel execution, and each one of those individual tasks become really fast. And so as you take a stream of data through your cluster, each task manager operates on its own, and each task operates on its own. And so it does one thing: filter, select, merge. Okay, and those things, this shared nothing architecture of Apache Flink is one of the key things that makes Flink a highly massive throughput at low latency. It's very, very good for that on streaming applications. And a job's broken down like this. What you're looking at here on your right this is a Flink SQL. So I'm sure, again, at this conference, everyone here is familiar with ANSI SQL. Congratulations if you've just learnt you're also a Flink developer. Flink supports ANSI SQL to do things. And so you can deploy a job just using SQL. And what this job here is very, very simple. It says insert into some kind of sink. Okay, some data that you have selected. For us, it's a time and a host name, CPU usage, from some kind of source. Okay, both that sink and source in our world are going to be Kafka topics. And the last thing is we're going to filter it just whenever the usage is above 80%. They're the only events that we want to process. And that breaks down from the job manager into this directed graph. And this is the job graph that sort of all Flink jobs tend to break down into. And you can see that it's got a selection stuff, it's got a source, it's got some kind of filtering, and it's got some kind of sink. It's got like an insert statement there. And that's how that gets broken down. Diving into Flink a little further, there's a number of different APIs you can use to create those job graphs. Okay, and we at Aiven, so at Aiven Flink, we support Flink SQL. But if you want to take Flink, the open source project, run your own clusters, do that kind of thing, you can deploy your own custom code into Flink. And you can use a number of different APIs to do that as well. So you can deploy either Flink SQL or use a code-based version of Flink SQL, something called the dynamic tables in code. You can go sort of one level below it and look at the data stream API. And there's sort of two streaming APIs that we can talk about, streams and windows. Or you can go right down to the lower level and talk about some of the real sort of low-level process function events kind of things, where you might want to get really complicated in your logic. The really nice thing about Flink is you can deploy a job with a mix of all these things. You don't have to go, okay, I'm going to use the process function. All my job has to be at that low level. So you can really choose which level of abstraction that you're looking at for each individual part of that graph is kind of useful. So let's talk about the 4 sort of main concepts that people tend to run into. You want to start to get your head across when you start to think about Apache Flink. The first concept is streams. Again, given the audience here today, everyone's probably fairly familiar with the concept of an event stream. Things happen in time, they stream in. Flink talks about bounded and unbounded streams. Okay, let's go back to our example we spoke about, all the cars on the Balti Bridge right now. At some stage, you have that as an unbounded stream. Cars are never going to stop driving across the bridge until the bridge falls down, I guess. But at some stage, like that's never going to happen. It's unbounded. It has no ending in time, okay? And that's stream processing, and it's typically more concerned with things like latency, things like state management is really important to think about because you have no end. So how are you going to think about if you're going to count or average things? Like you need to tell it that there's an end state. You're going to have to do that in blocks or sliding windows. And you need to think a lot about fault tolerance. Unbounded streams are quite interesting because they have no end. What happens when the cluster stops? Okay, in an unbounded stream that never finishes, no one has any technology that never stops. All right, at some stage, your Flink cluster will at very least have to be upgraded. They'll release new versions. You might want to push new versions of your app, or someone clumsy like me might walk past it and kick the power cord out. Right? It's technology. It's always going to happen. There's some really good primitives we'll talk about in a bit in Flink that support that. Flipping over that, you've got this concept of a bounded stream. A bounded stream is all the tags we read yesterday. All right, it has a start and an end date. And it's important to understand that in your data set because Flink offers you some really interesting optimizations. Inside, it'll pick up some optimizations itself, working on bounded streams. It also allows you to do things like filter and sort your data before you go in, and it will provide you with a much more predictable and consistent output because unbounded streams can quite often turn up with events out of order. We'll talk about time in a sec as well. So the first thing to remember is, first question you want to know is the data you're working on bounded or unbounded? The second thing you want to think about when you're thinking about Flink is your state. And one of the important things to understand about state is that it sits in memory at the task manager. And so you can think of state in this distributed cluster as like a sharded key value store. So you've got this stream of events, you're going to spread them out, you're going to process them in parallel, and they're all going to maintain this sort of individual state at each individual cluster, and then at the end, you can probably merge it in some kind of sync operation. What's important about that for someone that's designing Flink applications and deploying Flink clusters is that state can obviously impact how big your resources need to be. How big does the virtual machine that are going to run in this cluster need to be? What I'm doing today is I'm talking about a state of I think I've got 9 or 10 processes. It's taking a reading every second. We're calculating for 30 seconds and running an average, right? It's a pretty small in-memory state. But if you wanted to do this with 1 million processes over a week, the state that you want to hold in memory is going to be larger. Okay, so you have to have an understanding of how big is the state you need for the job that you need to run. And indeed, there's deployments of Flink out in the wide world that use state with terabytes, and they typically start to think about a different mechanism rather than running state in memory. They'll put it on some kind of file, off memory kind of storage, typically an object store or something like that. But there's ways around that. There's a trade-off there, of course. In-memory state is much faster. You're going to get a higher throughput than some out-of-memory state. So it's a good thing to think about. You want to understand how big is the operation going to be? How much data do I need to do? What am I counting? Welcome to what I think is my proudest moment of this presentation. I managed to find a picture of an actual timestamp. I was very thrilled when I found that. I didn't know those things existed. But time is a really interesting thing in stream processing, right? Because if you think about our IoT device example, I might have devices in Perth. I've deployed my Flink cluster on Azure in Melbourne, and I've got devices in Melbourne. There's a very real chance that an event will get generated in Melbourne that happens after the event that gets generated in Perth, but arrives at my Flink processor first. Events can arrive out of order once you get to this. There's a number of different things. This is one of those interesting things about stream processing. And so you can tell Flink, don't care about the order they arrive at the computer that I'm doing the processing. Look for an event time. This is the timestamp that's on the event the moment that it was created. Okay, this provides you with a much more consistent calculation because you can now say that my time window at the moment is 30 seconds, but I can tell Flink to wait. I think in my example, I'm waiting 10 seconds for each window. And it's basically like process in 30 seconds and then wait a few seconds for the laggard events to catch up. And I can put them into that state, that 30-second window. Okay, this will input. This can impact your throughput a little bit, but it will also give you better results on consistency. So the idea is like if you're taking a real-time stream processing approach and you take all those events, you'll get the same result as if you process them the next day for the same window. Now, it could be the case that that's not important to you. Throughput's a much more important thing. And so you can start to look at this thing called processing time or wall clock time. And that's the time on the Flink cluster. So as those events arrive, they'll get processed as they arrive at the cluster, and your 30-second window will be 30 seconds of wall clock time. Now, it could be then that you're going to get some events that sit outside that window. Okay, and so if you process them as a batch the next day, you might get a different result. It is a much simpler implementation to just think about processing time. So there's a thing in event time called watermarks, and it can get interesting. One of the things that we definitely tell, I know that I do when I'm building Flink applications, is if they don't work, because that happens, the first thing I'll do is I'll flip it over and look at see if it works if I've set it to processing time. It's like, have I made a mistake with my time? And one of the things that'll happen if you get your watermarks wrong is that Flink will just stop. The thing that happens will stop producing data. And you'll be like, I don't really know what's happening. And sometimes it's just waiting for time. The last thing to talk about is this inbuilt capability of snapshots. Snapshots is the fault tolerance mechanism of Flink. Okay, so there's two types of snapshots in Flink. There's the one that happens just without you doing anything at all. And so you'll have a stream of events coming into your cluster, and I think it's the job manager sits these things in and says, here's checkpoints. And a checkpoint is a marker on the event stream that tells the task managers, hey, when you get one of these things, put this in, take your state and copy it into a durable storage. And part of the state of the task manager is not only like the key value store that it's sitting on, but it's also the offset of the event that it's tracking on. And so if that task manager dies 5 events later, it knows that it has a state that it can restore to and continue. It just goes and finds the last event that we know that was stored in this durable storage, and we pick up and process again from there. That's what a checkpoint is. It's really optimized for quick recovery for the cluster. There's a manual snapshot in there as well, which is for those of us that have to operate these things in production, or you want to make sure that you can set a state and capture a state of your cluster if you're going to upgrade your Flink cluster or deploy a new version of your Flink application. You can say, hey, that's a save point, stop processing, do the needful, upgrade whatever I'm doing, start processing again. And that's how that kind of works. If you're super interested in the details here, how this globally consistent snapshot across a distributed key value store works, it's something called the Shandy-Lamport algorithm. That's all I know about it. I looked at it, I looked at that paper, and I went, I don't need to know that. But if you're one of those persons that is really interested in the detail, you can go and read that paper as well. I tend to trust people that do those things, that they've got them right. Okay, so let's look at what we're about to do. This is a really good indication of what we're going to do. So there's 3 kind of things happening here in our service that we've loaded up today. The first application we've deployed says, take the stream of data in. I'm running out of time. All right, take the stream of data in and then, filter it put it into another Kafka topic, and then carry on from there. Our second application then calculates the average over all those things that come in over 80. And the third one says, if we have something with an average of 30 seconds that's over 80, we need to alert someone. In this particular world, we're actually going to just put it back on an alerting topic in Kafka and leave the processing that to someone else. The last thing I'll say before I get out of here is that you notice you can also read data from like a Postgres database in here. So it's not like my heuristic is for any IoT sensor. My heuristic can now be for individual sensors, and those thresholds can be maintained in some Postgres data table. I'm getting the hurry up, so you'll have to come and see me later. Sorry. Last thing to say is just if you're interested in the demo that you didn't see, there's a link here to a GitHub repository. It's just a Terraform script, folks. All this stuff will just be automatically deployed via Terraform for you. And while I don't have yellow ducks, I do have $500 worth of credit. So feel free to snapshot away, and we'll share these as well. Thanks for your attention.